This is a podcast of Scripps Institution of Oceanography at UC San Diego. To learn more about how you can support Scripps, visit us online at scripps.ucsd.edu. Scientists say there is a 99% chance California will experience a magnitude 6.7 or greater earthquake sometime within the next 30 years. As the state braces for the inevitable, scientists at Scripps Institution of Oceanography at UC San Diego are making major improvements to one of the field's most fundamental tools, the seismometer, and developing early warning systems they hope will save lives when the expected finally happens. Scripps researcher Yehuda Bach, director of the California Spatial Reference Center, installed the first real-time global positioning system stations at Scripps's Pinyon Flats Earth Observation Facility in 2004. Today, the system consists of over 80 GPS stations throughout Southern California, offering a promising early warning system that could outrun seismic waves, giving cities precious seconds to prepare.
After we detect an event and disseminate the event to first responders, then they can use that information to, for example, shut down critical facilities like gas lines or slow down trains, such as has been demonstrated already in Japan. The crucial step is to be able to find somebody to accept this information and react basically in a predetermined automatic fashion if such an event occurs. We're now developing a methodology to determine the magnitude and the location of the event within seconds, and then set up a mechanism where this information could be assimilated.
In addition, Scripps researchers are giving seismometers a needed facelift using the most modern technology. New sensors, jointly designed and built by Scripps researchers Jose Otero, Mark Zumberg, and John Berger, could offer seismologists an instrument capable of producing clearer recordings of seismic movements than current seismometers. They can also better withstand the extreme environments that scientists must access to listen to Earth's rumblings.
The biggest motivation was there's a lot of seismometers on the market, but there's not very many broadband seismometers, so we wanted to develop a broadband seismometer that's easily attainable, because the current seismometer that everybody uses is no longer being made, and that's called the STS-1, developed by Strickeisen. And there's very few of them available on the market, and the few that are available on the market are starting to break down, and there's not very many people who could fix them. So don't really have the tools we need to perform the science we want to do. We could deploy this into boreholes, whereas most, like the STS-1, which is, you know, kind of the instrument everybody wants to use, can't really easily go down in a borehole. One, because you have these long electrical wires that connect the two, and when you use really long electrical wires, they start picking up noise from the environment. And more than that, a lot of boreholes are encased in metal. So if you have a lightning strike in the region, lightning tends to ground to anything that's metal, so if you have your instrument in there, your instrument's going to get fried. And you know, if you have a $130,000 instrument in a hole and it gets hit by lightning and it's destroyed, that's not a good day. This could get hit by lightning, it's not going to hurt it. Well, the fiber optic carries the light into the interferometer. There's two ways you could get light into the interferometer. You could go directly in it, so you could set the laser right up in front of the seismometer and perfectly align everything, make sure they're at the same heights. But the problem with that is the laser has to be right next to the seismometer. That won't work in a borehole. But if you put the laser far away, you can imagine fiber optic is like a hose, but instead of carrying water, it carries light. And you know, normally light scatters everywhere, but in a fiber optic, the light will follow the fiber perfectly and come out the other end. So we take the light from the laser through the fiber and to the seismometer, and it's as if the laser was right in front of the seismometer, when it's not really, it's really far away. We could place the seismometer, you know, a couple kilometers away from the laser and the optics, which is nice, because then you could, you know, use one laser, run a bunch of seismometers that are a few kilometers apart from each other down boreholes. If there's a large earthquake, say in Sumatra, like a magnitude 8 or 9, you're not going to detect that in San Diego. You're not going to feel it in San Diego, but surface waves will come through San Diego, and a quiet instrument will detect those surface waves a few hours after the earthquake here. If you have a noisier instrument, it's not going to see them.
By understanding how the Earth works around fault zones, scientists can get even closer to pinpointing the causes, strength, and locations of earthquakes, information vital to save lives. Scripps scientists continue to develop new earthquake monitoring systems to better understand earthquake triggers and to quickly detect the direction in which the destructive wave will travel, in hopes it can be outpaced before it arrives.
More looking at the structure of the Earth, more understanding how, seismic waves propagate through the Earth and what's down there is kind of the goal of this instrument. But naturally, a seismologist, why is it important to monitor earthquakes? Well, so we could get a better understanding and make the public more aware of the potential destruction we could create. I mean, if we understand how the earthquake works more, then we could understand, okay, well, we know the Earth might move this way, so what can we do to build a better building or something like that?
This has been a presentation of Scripps Institution of Oceanography at UC San Diego.